Many of the concepts that govern linear motion also apply to rotational motion. However, there are some new concepts in rotation that can be difficult to master. The Rotational Collisions Lab will introduce you to some of these concepts and give you a chance to use them to predict the outcome of a few complex interactions. This is rotational collisions. In 1966, more than 3 years before he landed on the moon, Neil Armstrong thought he understood rotational physics when he decided to separate his Gemini spacecraft from the Agena spacecraft. Unfortunately, he neglected to consider the result of the reduced rotational inertia the separation would cause. This almost resulted in disaster as his Gemini spacecraft started spinning faster and faster out of control. You might avoid a mistake like this if you do your best when asked to make predictions in this lab. We have mounted this wireless rotary motion sensor horizontally on a support rod. It measures the angular velocity of anything attached to the axle. We can remove the plastic pulley and attach a disc to the axle with this short screw. There is a longer screw that comes with the disc that is used for the last experiment. Don't mix them up. You'll try and predict what will happen when we drop an object on top of the spinning disc. Then we observe and measure the collision and learn from comparing your prediction to the actual outcome. We have two identical discs. We need to measure their mass and radius. That one's 106 grams. That one is also 106 grams. So each disc has a mass of 0.106 kilograms. And the radius is 4.5 centimeters or 0.045 meters. We also have a ring that has the same radius as the discs, but doesn't have the same mass. It's got this big hole in the middle, but it's thicker. So what do you think? Let's see. And it's 102 grams or 0.102 kilograms for the rings. Very close to the same mass. So when making predictions in this lab, it's okay to assume the ring has the same mass as a disc. Let's attach the disc to the rotary motion sensor and make our first prediction. And so to attach it, I again use the short screw. And I'm holding my finger on the axle so it doesn't spin, so I can tighten that screw so it doesn't slip. So it's on there really good. And just to give you an idea what the data looks like, this is our angular velocity time graph. If I hit start and give it a spin, it measures the angular speed in radians per second. If I spin it clockwise, it's a negative value. And so I'm going to try and spin it counterclockwise so everything's positive in the lab. That might make it a little easier. So in our first experiment, we're going to drop the second disc onto the first when it's spinning at about 10 radians per second. Your job is to predict whether the angular velocity of the bottom disc will increase, decrease, or remain the same. And if it's spinning at 10 radians per second when this lands, what will be the numerical value of the angular speed after they're spinning together, after the collision? Remember, each disc has the same mass and the same radius. If you want to avoid the mistake that Neil Armstrong made and others, make sure you make your prediction before you look at the graph of what happened in the data file. So don't look at it until you've written down your prediction. So you won't see this, but I'm collecting the data, spinning, slowing it down to around 10, and there we go. So we have the first collision. We want to have more data, so we're going to collect 4 more collisions. The first when the disk is spinning at about 20, then 30, 40, and finally 50 radians per second. You'll analyze this data when you get to this part in the lab handout. Now, chances are sometimes when I drop this, it's going to fall off. I won't get a good collision. I'm going to delete those runs if that happens And so when you get your data file, you're just going to see the runs where there was a good collision. Here we go. So this is run 3, or run 2, going at 20. Hey, what do you know about that? Okay. 30. 40. And finally 50, it's about as fast as you can spin it. Next, we'll see how to determine the angular speeds of interest from the graph. The data we need to measure is the angular speed just before the disk was dropped and the angular speed just after they started spinning together. On the angular speed graph, you'll see the line sloping down gently as friction slows the disk a little. Then you'll see a steeper slope as the disk that was dropped hits the bottom disk. Then the line will go back to a gentle slope as they're spinning together at the final speed. You need to measure the angular speed just before the steeper slope starts and just after it stops with the coordinate tool. Again, I'm not going to show you here because it gives things away, but you'll have this data. You'll be able to figure it out, and the lab handout helps you with this. After you complete your graph and analysis, you're asked to make another prediction. We're going to drop the ring onto the spinning disks. Predict whether the angular velocity will increase, decrease, or remain the same. Also, if the disk is spinning at 10 radians per second, what will be the numerical value of the speed right after the collision? Remember, the disk and the ring have the same mass and radius. It's okay to make an incorrect prediction, but if you look at the data before making your prediction, you won't learn much physics from this experiment. To help catch the ring, I'm attaching a small plastic alignment guide that has negligible mass. So I remove the screw, the small screw. Now run it through both the disc and the alignment guide. And so again, it just adds a little bit. Doesn't really alter the mass of the disc much. And so 10 radians per second. Slow down. It's about 15. Here we go. So again, the data's here when you're ready to check your prediction. After you check your prediction and answer a few questions, you will have learned a lot about the concept of rotational inertia, maybe even more than Neil Armstrong. Remember, it isn't important whether you predict correctly or not. What is important is that you made your best effort and learned from the experience. The lab handout will help you understand what actually happened. As a final test, it'll ask you to predict the outcome of the ring colliding with both disks, spinning together at 10 radians per second. I hope I don't have to remind you to make your prediction before you look at the data. So removing the short screw, now I need the long screw to be able to go through both disks and the alignment guide. So both disks will be spinning together at about 10 radians per second. And then we'll drop the ring on. So again, you're not going to see the data, but I am collecting it here. Going about 20. Let's slow down a little. Let the tension build. What's going to happen? It's about 15. Takes longer to slow down with both discs on there. There's some physics there. Here we go. There we go. So again, data's here for you to look at it once you're ready. If you can successfully predict the outcome of that experiment, I'd hand over the controls of my spacecraft to you any day. If you didn't predict it successfully, go back over the questions and analysis and try to find your mistake. That is what Neil Armstrong did after surviving the Gemini 8 disaster. What he learned from that process helped him land on the moon successfully.